Welcome to this explainer. Today we're unpacking the incredible, often completely invisible engineering that keeps massive modern freight networks moving safely. When we think of railroads, we usually just picture these massive steel machines from a bygone era. But actual modern rail? It's a highly sophisticated ecosystem. We're talking about a really delicate balance between heavy physical mechanics and cutting-edge digital data.
So how exactly do you safely move 30 automobiles, or say thousands of tons of toxic chemicals, across the entire country at 70 miles per hour? Let's dive right into this, because solving this massive physics problem required rail engineers to totally rethink both the physical cars we see rolling down the tracks and the digital signals we don't. I mean, moving that much weight at highway speeds is just an astonishing feat. To pull it off, the industry had to innovate from the ground up, tackling both the hardware carrying the load and the software keeping it on the rails.
Basically, modern rail is this intricate dance between massive physical hardware and invisible digital software. A modern train absolutely isn't just a 19th century hauling machine anymore. It is a wirelessly connected marvel of logistics. So we're going to look at this in two main parts today. First, the hardware, the specialized rail cars custom built for unique cargo. And second, the software, those invisible automated safety networks that ensure these massive machines don't collide.
Section 1. The evolution of autoracks. Let's start with that hardware, specifically looking at the really fascinating problem of transporting brand new, delicate automobiles from the factory to the dealership without a single scratch.
From the 1920s with standard boxcars holding maybe 2 to 4 cars, to the 1950s introducing bi-level flat cars, all the way to the fully enclosed tri-level racks of the 1970s. Look at how rapidly the industry had to innovate here. In the 20s, you were literally just stuffing a couple of cars into a boxcar. But as the auto industry exploded, railroads desperately needed scale, leading to those massive tri-level racks we'd actually recognize today.
Adding roofs and continuous side panels protected these valuable new vehicles from weather and vandalism. And this rapid evolution solved a massive financial nightmare. Back in the 1960s, open-air transit meant brand new cars were showing up at dealerships with broken windows, stolen parts, or severe weather damage. The solution? The fully enclosed autorack. By slapping on continuous side panels, end doors, and roofs, railroads essentially created these secure rolling garages that drastically reduced freight damage claims.
So how did General Motors and Southern Pacific manage to fit 30 Chevy Vegas into a single rail car? Well, automakers always want to push the limits to cut shipping costs, right? They wanted to pack even more vehicles into a single train car, and that drive led to one of the most bizarre and brilliant engineering feats of the 1970s, when GM partnered with Southern Pacific Railroad to do the seemingly impossible.
To pull this off, they needed special engine oil baffles to prevent leaks, repositioned battery filler caps, 45-degree angled washer bottles, and carburetor drain tubes routed into the vapor canister. Chevrolet actually had to completely redesign the Vega's internal fluids just so the cars could be shipped vertically, nose down. I mean, think about that for a second. They essentially re-engineered the car just so it could hang vertically on a train door that was open and closed by a forklift. Absolutely wild.
Compared to a conventional tri-level that held 18 standard automobiles horizontally, the Vertipack held 30 Chevy Vegas packed vertically, nose down. By packing them like this, they almost doubled their capacity. Now, while the Vertipack was retired after the Vega finished its run in the late 70s, it perfectly demonstrates the extreme lengths engineers will go to maximize rail efficiency and tailor their hardware to a highly specific product.
Modern multi-max autoracks are nearly 90 feet long and 19 feet tall, featuring adjustable decks for bi-level or tri-level configurations, accommodating up to 22 light trucks or minivans, all behind patented secure doors to eliminate theft. Today, this hardware has been perfected. What is just genius about these modern Titans is that they can adjust their internal decks right on site without even removing them. It lets the railroad easily switch configurations depending on whether a manufacturer is pumping out large trucks or smaller sedans that week.
Section 2. A car for every cargo. Now, autoracks are really just one piece of the puzzle here, so let's quickly look at the specific hardware used for other commodities across the massive freight network.
Looking at this breakdown of rail cars, you see well cars with deep depressions for double-stacked shipping containers, tank cars for liquid chemicals, gondolas with open tops for scrap metal, and covered hoppers with sloped floors for grain and cement. The hardware across the network is just perfectly tailored to its specific cargo.
The well car sits incredibly close to the rails so you can double-stack containers without hitting bridges. The tank car is essentially a massive, elongated barrel on wheels holding up to 31,000 gallons, and the covered hopper uses gravity-fed sloped floors to seamlessly unload free-flowing goods. It's all highly specialized.
Section 3. The push for rail safety. Okay, so now that we have all this specialized, incredibly heavy hardware speeding across the country, we have to tackle the invisible problem. How do we actually prevent catastrophic collisions? This brings us to the software and signaling side of our explainer.
We're comparing dark territory, which are unsignaled remote lines where crews rely on radio-transmitted track warrants, to signaled interlockings, which use track circuits and physical signals to dictate speed and right-of-way. Traditionally, trains navigated using visual signals, kind of like giant traffic lights, or they ran in completely dark territory. In dark territory, there are 0 signals. Dispatchers coordinate everything via radio warrants. So if an engineer missed a red signal or misunderstood a radio command, there is virtually no physical backup to stop a multi-ton train. It left a rather terrifying opening for human error.
The 2008 Metrolink collision and the 2015 Philadelphia derailment tragically proved that relying solely on crew compliance was no longer enough. That reliance on human compliance proved fatal over and over. Following those severe tragedies in Los Angeles and Philadelphia, Congress finally recognized this massive flaw. They passed the Rail Safety Improvement Act of 2008, mandating a massive, nationwide digital overhaul to physically prevent these types of accidents from ever happening again.
Section 4. Positive Train Control Explained. And this brings us right to the software half of our explainer, the invisible digital safety nets that govern the rails, universally known as Positive Train Control.
Positive Train Control, or PTC, is a family of automatic train protection systems designed to automatically track train positions, calculate safe braking curves, and forcefully stop a train if it exceeds speed limits or movement authority. The biggest takeaway here is that PTC is not just some beeping warning system. It actively overrides the human engineer. If a train is speeding toward a restricted zone or a stop signal, the onboard computer calculates exactly when to brake, and if the human doesn't do it, the computer automatically applies the penalty brakes to halt the train safely.
So how does it work? Well, transponders in the track send location data to the train. Onboard computers continuously calculate a safe braking curve. Radio systems update the train with temporary speed restrictions, and automatic penalty brakes apply if that curve is exceeded. Looking at a specific system like ACSOS on the Northeast Corridor, it's amazing. Transponders physically laid in the track tell the train exactly where it is. The onboard computer constantly calculates a safe braking curve based on weight and speed, while a radio network dynamically beams temporary restrictions straight to the cab. Cross that curve, and the software forcefully steps in.
ACSES guarantees redundancy through standby wayside communications managers if lightning strikes, continuously evaluating for the strongest radio talk path, using legacy continuous cab signals as a non-wireless backup, and reverting to permanent onboard database restrictions if completely disconnected. Because a system this critical literally cannot afford to go offline, the built-in failsafes are incredible. If lightning hits a tower, standby managers instantly kick in. Even if a local base station loses all power, the train's computer just seamlessly falls back on legacy electrical pulse codes sent right through the steel rails, or relies on its onboard database to keep everything safe.
As of December 2020, Positive Train Control is fully installed and operational on 100% of statutory required U.S. trackage. Implementing this required just an unbelievable amount of coordination, negotiating for radio spectrum, retrofitting tens of thousands of locomotives. The sheer scale of rolling this software out across the entire North American rail network is staggering. But as of 2020, this digital safety overlay is fully active everywhere it's required.
The modern railroad is a seamless integration of massive, specialized steel machinery guided by an invisible, heavily redundant wireless data network. Ultimately, those freight trains you see rolling by, they're actually moving data centers. They are a seamless integration of incredible, highly specialized hardware, like those shape-shifting auto racks, talking constantly with the tracks beneath them through a massive wireless network.
So as our massive freight trains become completely blanketed by autonomous safety software, how long until the human engineer becomes entirely obsolete? It leaves us with a pretty fascinating thought. We've solved the hardware by designing custom cars for everything from grain to the Chevy Vega, and now we're perfecting the software to mathematically prevent crashes. As these networks become fully governed by autonomous safety controls, what is the future of the human element in rail logistics? Will we always need an engineer in the cab, or are we looking at the dawn of the fully autonomous train? Definitely something to think about the next time you're waiting at a railroad crossing.